I'm going to revisit my look at the Regal DG-4102 Arbitrary and Function Generator. This is the unit that I talked about earlier. I've learned a few other things about it. I thought I'd pass those along. And on the screen you'll see a website where someone goes stepping through all of the functions this thing has as far as arbitrary waveforms. And since he's done a pretty good job of that, I figure you can go there and look at some of that. But I'm going to go back to the modulated signal levels from this generator, because that's more in my interest area of radio frequency, IF frequencies, and so forth. As you see, we have 1 kilohertz frequency at an amplitude of 5 volts peak to peak here. So I'm going to change the frequency here. You have a choice of period or frequency. We're going to make that 10.7 megahertz, a common IF frequency, 10.7 megahertz. Amplitude's a little high, I think, for what we want, so I'm going to go to, let's make it amplitude 1.3 volts RMS. Offset's fine, 0, and phase. So that's the frequency this thing should be putting out at that voltage level. However, I want to point out something here that I wasn't fully aware of. I have the spectrum analyzer over here hooked by this cable, and that cable happens to be a 50 ohm load on the spectrum analyzer. The source here on this T connector that I'm using here is the output of this generator, which is actually 50 ohms as well, roughly. And so there will be some attenuation of the signal because it's being divided, which will be viewable on the scope, which I have attached here on the other part of this T. We have no output at the moment because this output is not turned on. So I'm going to turn that output on. Okay. And if I go over here, you'll see that we have a bit of a problem at the moment. Well, the thing's not nagging me about the level here. It is off the top of the screen. So let's change the amplitude here, reference level, to 10 dBm. All right. And let's hit the peak here, and it's telling me that I'm actually at a level of 8.37 dBm. So let's put that peak up a little bit. Go back over to the ARB generator, and we'll go to amplitude. We're already on amplitude here. So what we will do is, rather than being on the 1 volt, we'll go over a couple of points here by using these arrow keys. And now I can run this up. I'm going to run it up until the spectrum analyzer says that it's 10 dBm. Well, okay, 8.99 dBm with 1.4 volts RMS according to this. I'll show you that. Okay, so we're at 8.98 dBm, which is, oh, that's interesting. Oh, I needed my glasses fixed. Okay, let's run this up to 10. There's 10.02. That's pretty close. So 10.02 dBm, which is actually 1.58 according to the output shown on this screen. But we sort of suspect that that isn't quite correct because of the impedance loading that's going on. Then we'll go over here and we'll see that we do have a carrier, as seen by the scope. And if we change the time base here, we'll go through some aliasing here, of course, but then we'll get to something that we can actually measure. There we go. Looks like we have a signal. Let's turn on the cursors. All right, and cursor, it's set up on time, so if I use this and go right at the crossover point here, which looks to be about there, and use this to go to the crossover point here. As long as you use the same point, it's okay. And it says that we're at 10.78 megahertz, so we're 80 kilohertz off relative to what this thing thinks that frequency is. But of course, the Spectrum Analyzer, which has a little better time base, says that it's 10.70168 or 666. Now I can probably improve on that a little bit, because this, of course, doesn't have a very sharp nose on it here. So if I go to the bandwidth here and change it from 30 kilohertz to say 1 kilohertz, now I have a very sharp point. And if I hit the peak on that, it's going to tell me it's 10.7000000. That's a little bit closer to the reality that I'd like to see. And so it's quite accurate, obviously. And I don't even have the sweep here set to the accuracy position, which would slow the sweep down a little bit more and provide a little more accuracy. But I think that we're okay with what we got frequency-wise. Let's go to frequency here. Yeah, 10.70000. Good enough. All right, back to the Regal 4102 here. I want to modulate this, so I'll go to Modulate. Right now it's showing that it's modulated, but it's 100 hertz, as you can see, and I think that I'd rather have something more like 1 kilohertz, so I'm going to go to AM frequency here, which is what they call a modulation frequency. I don't know why they chose that set of terms, but that's what they did. 1 kilohertz. So we're AM, internal, 1 kilohertz sine wave, and the depth's been set to 100%. And let's go back over here to the Spectrum Analyzer. Well, we're not really seeing that modulation, but then again, we don't have the resolution set, or the span set quite narrow enough here, so I'll hit span here. Let's make that 10 kilohertz. Well, 100 kilohertz. And I still don't see it too well. Let's go to 10 kilohertz like I originally said. Now, the problem here is that we are not getting what we want to get on this because our resolution bandwidth is not good enough. So we are going to have to set that manually here. The resolution bandwidth has been manually set. If I go to auto, it clears it up somewhat, puts it at 300 hertz, and so you can easily see the two sidebands there. I think I'd rather go to manual here and 100 hertz. It's going to slow the speed down, but it's going to give us a little better depth on the modulation there. So there's your 1 kilohertz video bandwidth, and you have Well, let's do this. Let's go to peak. Let's go to the second screen here in the peak table. Let's find out what these frequencies are. Turn that on. Now I've got 3 peaks showing up. One's at -2 dBm. The other one's at -2 dBm, and then the center frequency is 16 hertz off and at 3.84 dBm. So there's about 6 dB between the peak and each sideband, which is what you'd expect with an AM signal that's 100% modulated. Okay. Now let's look over on our scope over here. Well, that doesn't look quite right. But that's because that's where it's being triggered. And what we need to do to see the modulation, of course, is to creep down here. Ah, yes, much better. The last time I did this, that was creeping through and I had to run stop to look at that waveform. But what I discovered and had forgotten, because I had not been using this type of a scope for a while, is what you've got to do, especially on a digital scope, is to hit your trigger and then hit your hold off. I put it on auto and I just adjusted this. It'll grab the RF frequencies unless you use the hold off to make it look there and then there. So it might trigger here and it might trigger there, as opposed to triggering there and on the next cycle or something. And that's why it's stable now. So it's worked out pretty well. The on here also, after a while, the stuff that was on the side here will go away by itself, depending on where you set it. I set it fairly long, about 20 seconds or something, but some people just have it for a few seconds. All right, so there we go. We have 1 kilohertz sine wave, and it's 100% modulated. There's one other thing that you can do with this particular unit that's fairly useful, and that is, if I go down here, I see something that says DSSC. That's double sideband, which is what we have, except suppressed carrier in this case. And what we have, of course, is normal AM, which is non-suppressed carrier. So if I push this button, what should happen is it should change. I have to push it twice to select it and then push it a second time. Change to a different modulation, which is suppressed carrier double sideband, which should look like that. And, in fact, it does look like that. And over here, of course, it looks like we had before, only the carrier is now missing. So that's the way that works. Our receive bandwidth actually did not change the last time. It should be 100 hertz. All right, much better. Sometimes I have to, pay attention to what I'm doing here, because these cheaper instruments have buttons that don't necessarily punch when you think you've punched them. That's what apparently happened, or else I might have just stuck it over on auto and it would have gone back to 300 kilohertz. So at 100 kilohertz, we quite easily see the 2 peaks here. Notice that the peaks have gone up to the same level as 3.71 or so that we had for the carrier on the AM. That's one thing about this arbitrary generator that's sort of interesting. It doesn't modulate 100% modulation on the carrier that you have. The peak is set to the same level in either case. So if I change this thing by, let me do it here, turn off that, you'll notice that this now comes up to that level, and these guys are down by 6 dB. So apparently it's looking at the peak of the envelope, not at the actual carrier level. And that's, I don't know if you want to call it a failing or a difference, let's say, between this and, say, a signal generator, which should have the peak envelope power go up. And so just something to note, that you've got to probably use the scope to measure what you're doing. I would also like to note that these are all below 40 dB down, below this. And the other thing, I'll put this back on over here to DSC, come back over here. Let's see if we can get 10 dBm per tone. What I'll have to do for that, let me crank this over here. And if I crank, if I get sine wave again here, and I'm already on the amplitude, as you can see here. If I crank that up some more, I can push that up to 10.76, so slightly above 10 dBm per tone. And you notice that we still don't have any distortion based on the two tones here. Everything else is just noise, and that's what's peaking around -40 now. And that's actual noise of the, I would presume it's of the 4102 here. It's 40 dB down. But anyway, the point is that you don't have intermod products out here and out here, out here and out here. So it's very clean signal, and one that I would think would be very useful for a source in an IF amplifier, especially linear type amplifier that you want to look at linearity and so forth. As far as modulation is concerned, we do have other things that we can use for modulation. I press this again. We can change this source to external from internal if we want, and put in any kind of waveform. But let's look at shape. What do we have for shapes? We have the sine wave. We've seen that. There's a square wave. And the square wave with double sideband is going to show the harmonics of each of these tones, because it is a square wave after all. And of course, because it's double sideband, it's going to have sidebands out of phase, so it pretty much looks like a solid line. And here's the harmonics. So the harmonics of this one are going up, and the harmonics of that one are going down, or subharmonics, whatever you want to call it. And that's because of the square wave nature of what we're putting into this thing. All right, go back here to see what we have else. We have shape, triangle wave. All right, there's what we have for the triangle wave. And those are the harmonics of the modulating tones that make up a triangle wave. And here's what the waveform looks like over here. Looks like triangles. Now we also have, now this is still double sideband, mind you. We also have some others on here. What else do we have? We have shape, up ramp and down ramp. Those are going to look pretty much like triangles. We have noise, so let's see what noise looks like. Now let's take a look over here. Yes, pretty much what it looks like. And we'll look over here, and as you see, since it's noise, it's spread all over the spectrum, so everything is down from what it was before on the double sideband signal suppressed carrier. And then one last one we'll look at here in the double sideband suppressed carrier mode will be the next one down. Well, shape. Next one down is arbitrary. which is just a little pulse in the middle like that. And here's what it looks like as far as the envelope is concerned. Looks like it's jittering a little bit there. And here's what it looks like spectrum-wise. So we're in the same ballpark. All right. Now let's go back and change it to AM from double sideband. So we'll turn that off. It's off now. And looks pretty much the same in both cases here. We'll go back to modulation shape, and we'll go to square wave. Oh, I see I didn't get the DSSC turned off here. There, it's off. All right, so now the AM looks just like you'd expect for a square wave. And you'd expect it to splatter all over the place like it does. Notice that the third is way down. Here's the first harmonic, if you wish. The second is suppressed. The third's there. The fourth is suppressed, and the fifth is up here. So that's what we'd expect out of a square wave. All right, let's go to shape, triangle. Yeah, once again, they've got the same kind of triangle waveform there, but with carrier in this case. Come back over here, still looks like a triangle. And we'll go to a ramp here, shape, up ramp. You see it spreads out more. If you look at the spectrum here, and if you look at the envelope, it looks like a ramp, up ramp. Then the down ramp, looks like a down ramp. Isn't that just fine? And the spectrum again is spread out due to the harmonics content of that waveform. And we can come back to here and put it on noise. So shape and noise. And that's the noise. This time it will have a full carrier, but you don't see much of the noise because it's the average noise is down pretty low because of the random nature of the noise. And we will also take a look at the shape arb, which looks like that, and has a spectrum like that. So I'll stop here. We'll do some more stuff with just standard waveforms. There is another video somewhere on YouTube that shows a lot of the different waveforms, and you might look that up. And I'll put it in the text when I upload this.